new material before the exam. You'll have a quiz Tuesday, which I will post sometime after class. Yes, and the office hours today are a little bit, I sent you all an email about that because I've got a master's defense. But anyway, we'll have a quiz that'll be due on Tuesday, probably at 8 o'clock, and one due Friday. Then, of course, you've got your exam Monday. You will not have a quiz due till Thanksgiving, obviously. So, okay, let's, oh, I wanted to start right here with this. If I have to find null space here, you get this matrix here, we're going to 2 by 3 matrix. You can rover this, so you get this. Everybody cool with that? And everybody agree this is rover this echelon form. So at this point, I would have I've got 2 basic variables, X1 and X2, and 1 free variable, X3, right? So the typical element of the null space is a multiple of this vector here. Everybody agree? What does this mean? This means this matrix times this vector is 0, right? And in particular, this matrix times this vector is 0 too. Notice this times this is -2 minus 1 plus 3 is 0. The second row, -1, 0, plus 1, 0. Everybody agree with that? That means when you take the dot product of the first row in this column, you get 0, and the dot product here, you get 0. Everybody agree with that? And this, I hope, explains a little bit of that last statement I made. Remember what the perp is, that's the stuff that is orthogonal, right, to everything in, to everything in the row space of A, right? What is the stuff that's orthogonal? It's the stuff that gives you a dot product of 0. This is the vector. Any multiple of this gives you a dot product of 0 with both of these, and that's why this is true. Everybody okay with that? Okay, so let's dig a little bit further into this. Let me give you a definition that I'll add a little bit to. D1, D2, up to DK and Rn are orthogonal if, what do I mean to have a set of vectors orthogonal? They all sit at right angles to each other as long as they're different. If BI is perpendicular to BJ for all I not equal to J, or in our more fancy modern terminology, the dot product of any pair of them give you 0. Right? The orthogonal set B1 up to DK is orthonormal orthonormal means orthogonal and then something else. Anybody know what it is? How many of you have ever heard the terminology normalize something? Right? It's sort of like you scale something to 1 often. If additionally each VI is 1. So it's orthonormal. Orthogonal, they sit at right angles. They're orthonormal if they sit at right angles and they're also all of length 1. Okay, so by the way, and we're going to talk about something called orthonormal bases. They're very important. Can anybody give me an orthonormal basis for Rn? On a basis that every pair of them sits at right angles are all length one. Yes.
Identity matrix of n elements.
Well, you mean the
And
columns
rows.
from them?
Yeah.
Yes. Everybody remember what I mean by that? E1 is 1, and then the rest zeros. E2 is 0, 1, and then the rest 0, and so forth, right? These all, it's very easy to see their dot type is 0, so they all sit at right angles, and they're all length 1 because they're full of zeros except for 1, 1. Everybody agree with that? Here's another example, not of orthogonal, or not of orthonormal, but of orthogonal. This right here. 1, 1, 2. -1, -1, 1. And then 1 - 1, 0 is an orthogonal set. And again, I really dig the dot type because it makes it easy to tell. What happens when I dot these two? -1 and -1, -2, +2, 0. So these two sit at a right angle, right? If you dot the two ends, you get 1 - 1, no 0, so you get 0. And finally, if you dot these two right here, you get -1, +1, 0. So these all three sit at right angle. This is totally not clear, just looking at them, right? I mean, can you all imagine this really quickly in 3D space? But all three of them sit at right angles, right? Which is kind of cool. Is this an orthonormal set? Yes. Yep. Well, what's the length of this one?
Not one.
Not 1. So these are not orthonormal. Can I fix it? Can I make it orthonormal? Sure. To make it orthonormal, all you got to do is divide out by the length. Right? This is like that thing we did last time about finding unit vectors. The length of this four, 5, 6. The length of this is radical 6. Square, square, square. 1, 2, 3. The length of this is radical 3. And the length of this is radical 2. Everybody agree? So I can make this orthonormal. Uh, 1 over radical 5, 1 over radical 5, 2 over radical 5, and then -1 over radical 3, -1 over radical 3, 1 over radical 3, and finally 1 over radical 2, -1 over radical 2, 0.
Would the first one be 1 over radical 6?
Yes, I completely, sorry, bit of a flashback there. 6, 6, 6. There we go. Oh, that was pretty easy. Any questions? Okay, here is kind of the first big theorem that we have on this business about orthogonal stuff. Yeah. B1, B2, BK is an orthogonal set then it is a linearly independent set. So linear independence is even stronger than orthogonal. If you have any orthogonal set, it has to be linearly independent. If you have a linearly independent set, it doesn't have to be orthogonal. Just take the vector 1, 0, and 1, 1, right? Those two are linearly independent because they're not on the same line, but they're certainly don't sit at right angles, right? However, we're going to find out that if you have any linearly independent set, you can tweak it. You can adjust it to make it orthogonal. But if you have if you have an orthogonal set that you just find on the street, it's automatically linearly independent. So it's a basis for the space spans. Why is this true? Well, suppose this is old school linear independent. What do I have to prove? Prove that that's a linearly independent set. What has to be true of all the C's? Zero. All the C's have to be zero. Good, right? So you know what I'm going to do? I'm going to prove that every one of those C's has to be zero. I am going to dot both sides by VI. So when I dot this, I get C1 VI dot V1 plus C2 VI dot V2 plus CI VI dot VI CK VI and what happens when I dot zero VI? Dot any vector with zero vector, zero. And actually, as I was doing this, I realized I needed to say something else. So I really forgot to say this, and maybe your book did too, although I got it, I might skipped over it. You have to assume that none of these are zero, right? Otherwise, I mean, certainly you could put zero in an orthogonal set, zeros are orthogonal to everything, but let's not do that. That's a no-no. And you'll see where that comes out. Now, let me ask you this. What happens when I dot VI and V1? What do I get? These sets, this is an orthogonal set of vectors, so everything VI and V1 are different, so you have to get zero in the dot product, right? Because they said, in fact, what happens when I dot these two? I get zero. In fact, when I dot VI with anything, I get zero with one exception. When I dot VI with the cell, why do I not get zero?
Guys,
That is correct. Well, actually the square of it, but that's right. Remember, when you dot a vector with itself, it's zero if and only if the vector is zero. See, that's why I needed that here, right? This is not zero. And so this whole thing, there's zeros everywhere. It's a huge mess of zeros. And I don't know why I wrote zero vector here. Just realized that too. You dot the zero vector with VI, you get the number zero. And what I get now is CI VI dot VI is equal to zero. And this is not zero. So if Bill times Fred is zero, and Fred is not zero, what's true of Bill? Must be zero. So what I've shown in this is every single one of those CI systems, right? Any of them, right? So this is linearly in. Okay. Any questions on? Let me give you a definition, and I bet you can even guess what the definition is when I start to tell you. Definition, let B1, B2, BK be a basis for W, a subspace of Rn. If the basis is orthogonal, we call it an orthogonal basis, right? What a shock. We say it is orthonormal if it is orthogonal and the length of each DI Okay, questions on that? Now, here's kind of one of the, I hope we'll start to shed a little bit of light on why orthogonal bases and orthonormal is even better, have utilitarian uses. So let me give you the following theorem. Let us suppose that let W be a subspace. Of Rn. We'll say with orthogonal basis. Be one. So suppose we have a situation. We have your favorite subspace, say it's spanned by D1 up to DK. And suppose you're so lucky that you have the D1 up to DK as an orthogonal basis. Okay, what's the importance of basis? Well, suppose you pick a random vector out of W. Okay. The big deal about basis is any W that I pick out of there at random is a linear combination of those BI, right? Now, of course, the real annoyance is what are the C's, right? What are the weights? What do I multiply B1 by, B2 by, B3 by, and so forth to make them add up exactly to W? This is a linear algebra problem that you could set down and you could find some huge matrix and work it out, right? Any volunteers? Nobody wants to do that, right? For orthogonal basis, there's an easy way to figure out what each one of those C's is, right? And in fact, each C is equal to here's what, instead of doing some kind of linear algebra thing where you figure out all the coefficients at once, you can do this. Whatever W is, if you want to know what CI is, just dot W with CI and divide by the square of the length of W. So another way to think of this is W dot VI over the length of VI. That is super cool. Because, first of all, it's quicker than setting up some huge thing of equations where you try to figure everything out. And I'll show you sort of practically how it works. And number two, you don't have to figure out the rest of them to get any individual CI, right? This works for C1, C2, and CI. So you can find an individual. And let me show you why this is true. And this is just a computation. If you look at W dot VI, well, that's this thing dot VI. C1 V1 dot VI. CI VI dot VI. All the way up to CK DK dot VI. Everybody okay with that? And this is a freaking bloodbath, right? Because every one of these dot products is zero except for that one. Everybody agree with that? All of them dead. So when the dust clears, what I have is W dot VI on the left side, and that's just a number. And on the other side, I have CI times VI dot VI, another number. And since this is a basis, V is not the zero vector, so I get CI is equal to W dot VI over VI dot VI, as promised. Now, let me give you a practical example. I want us to take a look at what we'd have to do otherwise. It turns out that here's the example I had earlier. This by the way, let's like to divide some basis. This is the example I used earlier. The only thing I recall showing is this is actually an orthogonal set. How many things do I have in this set? 3. Everybody agree? And what's true about this orthogonal set? Since they're all orthogonal, those 3 are what? Linearly independent. And if you have a set of 3 linearly independent things in R3, it must be a basis. So this has to be a basis. So this is an honest to goodness orthogonal basis. Agreed? Now let's suppose that I want to write, say, I can't believe I left there was 734, I think. Write W and turn basis. Okay, I want to write that. Right. You guys see how to do this, right? I mean, in the old days, what we would do is 734 is A times 112 plus B times -1 plus C 1 minus 1 0, right? That gives 3 equations and 3 unknowns. So we'd have to hope the system is consistent, reduce the matrix, all this. Nobody wants to do that, do they? Right? So 3 equations and 3 unknowns to find B, right? And by the way, what if instead of R3, I pick R17, right? 17 equations, so nobody wants that. But check this out. Let's call this, just for convenience. Let's call these vectors separately in order V1, V2, V3. What's W dot V1? Which one does you have?
738.
Oh, 7, 3, and 8, so it's 18, right?
Yeah.
And what's V1 dot of itself? 6. Right? What's W dotted with V2? -6. That look right? V2 dotted with itself? Looks like it's 3, if I agree. And W dotted with V3. Well, that should be just 4, right? And V3 dotted with itself? 2. So the coefficients, one for B1 should be 18 over 6. It's 3. This should be -6 over 3, and it's -2. And this should be 4 over 2, which is 2. And there we go. So W, which is 734, should be 3 times 112 minus 2 times -1 minus 1 plus 2 times 1 minus 1 0. Much easier than solving 3 equations and 3 unknowns, right? And actually, I could have gotten, if I only needed to know what the coefficient for this one is, all I had to do is one computation. Any questions on that? Okay. So there's sort of the utility of this. We're gonna go a little bit further into the geometry of this problem. Often it's convenient in applications to decompose a vector into perpendicular components. How many of you have ever had to do this before? Had you did this in physics class? Anybody? You know, you might have some force vector here, and you need to decompose this like into perpendicular components. Ever had to do that before? If you're an engineer, if you haven't already, you will. I pretty much guarantee you. This is the key to a lot of statics problems and things like this. So we're gonna do this here, so here's kind of, what we're gonna talk about, so. If we have. Suppose I'm given two vectors, y and u. I'll call this one u. And this one y. Often what I might want to do to get started in tackling this problem is find what we call the vector projection of y on u. So extend u out to a line, both directions if necessary. And imagine that u is the ground and the sun is up here. If it shines down at noon, you'll get this right angle here. And this vector here, which is a lengthening of u, we're going to call y hat, which is the vector projection of y onto the vector. I'm going to show you how we build this. We're going to get a nice little formula. So I've got some vector y that projects onto u. Just imagine that the sun blasts down to it. This is called a projection. More generally, you can project onto a space as well. So in other words, if you have, let's see how well I can draw this. Imagine you have kind of a plane here coming out of the board. And you have some vector here, y. Instead of projecting it just onto a vector, you might project it down into space here, like this. Right, so the vector projection of y onto the subspace would just be what we have going on here. We're going to talk about this more generally next time. Well, let's start with a simple one. How do we project a vector onto another vector? Well, for the purposes of trying to figure this out, I'm going to draw this flat to make it easy. Let's suppose this is a vector u. Suppose this is y. This vector here is y hat. The vector projection of the vector y on the vector. Everybody get the picture here? Now this thing's supposed to be a vector. And let me kind of describe it to you in words. This vector should be parallel to u. So it's on the same line u is, parallel to u. But it should have the length of the shadow, right? It should have this length right here. Right here. So how do I get the length of the shadow? Well, it's some old-fashioned trigonometry. Suppose this is the line, the angle between them. It's u. Does anybody remember when we talked about the angles between vectors last time? Anybody remember another way to write y dot u in terms of that angle? Ring a bell? Remember that one? So, given this picture, what's the length of y hat? Just from old-fashioned trigonometry, it should be, well, it should be the length of y times cosine theta. Everybody agree with that? But the length of y times cosine theta is y dot u over the length of u. U is length of y. So I want a vector in the direction of u that has length this, right? So what should I do? Should I multiply? I should take, let's see what, I want it to have this appropriate length, so it should be y dot u over the length of u. That's a number times the vector u. Is that right? Spoiler, it's not necessarily right. Right, spot was wrong with it. This is a number times the vector u, it's in the direction of u, right? But I want this to be the length. What's the problem? Potential problem here? The length of u might not be 1, right? So I need to divide by the length of u here. So this, I meant to say vector projection. So y hat is y dot u over the length of u squared times u. And the way your book writes it, which is also it's good to know it this way. That's a number, and this is the times the vector. And this will be of exactly the length of the shadow. By the way, the shadow is sometimes called the scalar projection in the direction of u. Okay. So here's a concrete numerical example. Find projection y hat of y equals let's say 1, 2, 3 on u, which we'll say is 2 minus 1. By the way, what do you suppose the projection will be if these vectors happen to be at right angles to each other? It'd be 0, right? Because there's no shadow in a certain sense, right? What happens if these vectors are on the same line? Or if they're parallel? It should be just, yeah, it should just be y. So let's see what happens here. It should be y dot u over u dot u times the vector. So let's take this apart. Y dot u. Well, it's going to be 3 minus 2 is 1 plus 6 is 6. Put things right there. Oh, no, I don't know where I put it here. Let me try that again. 2 minus 2 is 0, 56. There you go. Off a little bit. And u dot u That should be 4, 6, 7. Or 4, 8, 9. There we go. There we go. 4 and 4 is 8. So this should be, in this case, it should be just 2/3 of what the original vector is. Which in this case would be 4/3 minus 2/3. Everybody okay with that? Okay. Any questions? Okay, so here's we're going to talk more about vector projections tomorrow on kind of a larger scale, and learn how to kind of decompose things into a nicer basis. But let me tell you something about what we call orthogonal matrices first. There. Okay, I'm going to start here with an n by n matrix. You have orthonormal columns. If and only if let's see, I want U transpose times U. Gosh, I'm not even gonna write the punchline. Let's see if we can figure this out. So let's call the columns U1, U2, U3, all the way up to UN. Right, because if U is in n by n, it should have n columns. Can you like tell me what happens when you? I'm not going to try to write U transpose, because what happens is it turns these columns, it turns this first column of this matrix into the first row of U transpose, the second column of this matrix, second row of U transpose, and so forth. By the way, somebody tell me, what's the size of U transpose something?
4 by 4.
What is it?
4 by 4, or I guess side by side, and by
N by n. This should be n by n. What happens to what's the first entry? How do you make the first? I shouldn't say first. The 1 entry of this first row, first column should be the first row of this times the first column of this, right? So this should be U1 transpose times U1, right? It's another name for this. It's the dot product of U1 with itself. What should the second entry here be? Well, it should be the second row of this times the first column of this, right? Second row, first column should be here. Right. So this should be, oh, wait a minute, let's see here. No, I'm going through this wrong. So I should have U1 transpose U1 transpose U3. And finally, U1 transpose UN. Everybody agree with that? Now down here, I get the second row of this, which is U2 transpose U1, U2 transpose, U2, U2 transpose, U3, U2 transpose, UN, all the way down to UN transpose, U1, UN transpose, U2, UN transpose, UN. Now, since the columns are orthonormal, what happens to most of these entries? Most of them are zero, because isn't this the dot product of U1 and U2? Which is zero. This is the dot product also of U1 and U2 in a different order, it's zero. And in fact, what are the only things that survive?
The diagonal.
The diagonals are the only ones that survive. And so what you end up with is U1 dot U1, writing it in the parlance of our times, U2 dot U2, UN dot UN. Correct? Now, these are orthonormal, so what's true of these? Well, they're all one, right? When you dot it with itself, right? Yeah, I have. Here's another theorem along these same kind of lines. I won't go through the proof of this, but this might be a kind of a good exercise. So you can figure out why this is true. You know, if you, again, n by n matrix, but if in general, have orthonormal columns, and x vector and y vector are in Rn, then actually Ux is in Rm. And X is in Rn, but they have the same size. Two, Ux dot Uy is equal to X dot Y. And so in particular, what this means, Ux dot Uy equals 0 if and only if X dot Y. And so what this means is so the linear transformation T from Rn to Rm given by T of the vector X is equal to Ux preserves lengths of vectors and orthogonality. This is a rather important property for a linear transformation to have. It's exceedingly nice because the size of your input vector is equal to the size of your output vector, and you sit at right angles if and only if the original vector is set at right angles. And so in the special case where n and m are the same, so if you've got a square matrix, definition, and I must apologize for this definition. A square matrix U in R n by n that has orthonormal columns is called, if I want to guess, what do you suppose you call a matrix with orthonormal columns?
Linearly independent.
I would go with that, orthonormal. Unfortunately, somebody dropped the ball on this, and it's called classically orthogonal. And I apologize for that, but when it's orthogonal, it means the columns are orthonormal, even though an orthogonal set doesn't have to be that. Anyway, go figure, but we've got to learn the language. Let me point out that in this case, another equivalent definition of orthogonal is the transpose of the matrix is the inverse. So an orthogonal matrix is a square matrix it has to be invertible, obviously, and it transposes its inverse. Okay, any questions? All right, y'all have a good one, and we will see you on Wednesday.